Now, item B, intrinsic geometry, exterior algebra in 3D. In this case here is a 2-dimension. Now, B part 2, lecture 10, a vector field. Transform its components. Previous videos showed transforming its basis. Now, transform its components. Now, 1. From Cartesian space to the polar space. Example setup. Let's use the point xy, square root of 3 and 1. Then we can obtain r, the square root of s squared per y squared, which leads to equal 2. Also, theta is the inverse tangent of pi over x, which is pi over 6. See? So, cosine pi over 6, square root of 2, sine 1/2. Now, start with the vector field in Cartesian coordinates. You see, Cartesian coordinates in this example, they are given. Then, in this case, the components belong to these polar coordinates are the unknowns. So this is a numerical problem. Now, attention now, Vx partial x, Vy partial y. Now it's given, you see, Vx is equal 6 and Vy is equal 4. We want to express these polar coordinates that's invariant. You see the same V, okay? This is Vr, partial r, partial respect to r, and V theta, partial respect to V theta. Now, important foundation. Attention now. Let's recall a vector field is invariant. See, this is the vector field V, okay, with respect to the Cartesian coordinates. This is a vector V with respect to the polar coordinate. It's the same vector, is invariant. Now, from the previous lecture 9, okay, the relation between the basis, okay, belongs to the polar coordinate is given by cosine sine minus r sine r cosine, partial of x with respect to y. So this is a relation that leads to this components of this vector over here, the basis vector. See, just to copy from lecture 9 to here. Now, equate the vector field expression. And now is a vector field. You see, look at here. This left-hand side is equal to the right-hand side. You see? Now Vx, just substitute. You see? Now, from here, we have to plug these components over here, okay? This is Vr cosine theta minus V theta r sine theta partial x. You see? Attention now. This here comes from this base vector here with respect to the Cartesian coordinates. Likewise, partial Vy. So you just repeat and plug over here. You see? You substitute. You go lecture 9, get the relation, okay, and then substitute over here. It's quite easy. Now you can group partial x and partial y. So this leads to easily, you see, Vx is this parenthesis over here, and Vy is equal this parenthesis over here. So it's just easy. Now, polar to Cartesian. You see, when you say polar to Cartesian, the right-hand side must be given, which is the polar. You see, look, the right-hand side, you see, if you write polar to Cartesian, the right-hand side is related only to the polar coordinates. The left-hand side is Cartesian. That's why you write polar to Cartesian. Now, recall from the electron, you just go there and copy. Just plug here. You see, this I call J, capital J, is Jacobian. This is a basis related to the Cartesian coordinates. You just copy and put, let's call this Jacobian. Analogously, from lecture 9 again, you see, you get the relation between the basis, the Cartesian basis, to the polar basis. Just copy from there and plug over here. See, this I will call, if you look at here, you look at J, you see, if you find the inverse of J, not this J transpose, if you find the inverse of J, you lead to this relation over here, okay? Now, also you can go lecture 9 and copy this, you call the matrix M, which is J to the minus 1, okay? You find J, not transpose, you find J, you see that this is the inverse of the Jacobian, I call M, see? Now, this is equal to VR and V theta, you see? So this attention now, which is very, very interesting. When I relate components, you look at this M over here, this is exactly M transpose, okay? Just observation, you see? You look at this M here, which is the inverse of the Jacobian, you call M, and there's the relation between the bases here is, you call here M transpose, see? So this is M transpose. Now, M transpose relate components, you see? That's important. And M relates bases. See, bases, this is components. Okay, now the numerical example. For I is equal to, theta is equal to pi over 6, then the input data, VR is equal to 3, V theta is equal to 1. They belong, attention now, to the polar coordinates over here. See? Now, let's compute Vx, Vy that belongs to the Cartesian coordinate. You just write down, you say Vx, Vy, you see cosine minus sine, sine and r cosine, Vr and V theta. This one is written over here. You see here? You copy from here, you just plug it there. Okay? It's good for you to recall. This is J, attention now, this is J transpose. See? Just look at here and copy and set there. Now, then I can multiply this matrix, 2 by 2 matrix by 2 by 1. This is this case, first row in the column. So you calculate, you have all this data, this will be approximately 1.6. So Vx is what I want. I want the x component of the vector V. It's Vx approximately 1.6. Likewise, I substitute all the data here. This is Vy. Vy is equal to 3/1/2 minus 1 square root of 3 over 2 is approximately 3.2. Now I want to compute, okay, given x and y, let's compute Vr and V theta. This belongs to the polar coordinates. This I have to know the components 6 and 4. See? So then I can write, attention now, Vr V theta, see, cosine, sine, minus, and cosine. Attention now. See, this I just copy from here. See, everything is written over here. So I have Vx and Vy, and I can obtain cosine and sine in R. See, R is 2. Cosine of pi over 6 is square root of 2. And sine is 1/2. So I have all the data to calculate the components of vector V, okay, in the polar coordinates. Just substitute numbers. See, this is R, cosine of theta, square root of 3 divided by 2, theta is equal to pi over 6. So I just substitute here, then I multiply this 2 by 2 matrix by this vector, 2, 1. So this is approximately 7.2, and V theta is approximately this case is minus here, okay, minus 0.2. You see, because the square root of 3 is 1.732, and this here is minus 1/2. That's why, I'm sorry, this will be plus. See, I subtract this minus this is plus 0.2. That's it. See, this is a numerical application, okay? Just obtaining basis, relation, and also components, okay, of a vector. That's it.